This is a pleasure to introduce the next speaker, David Massey. He's from Northeastern University, and he is speaking about non-isolated hypersurface singularities, stratifications, and delay cycles. He is one of the main researchers of non-isolated hypersurface singularities.
Thank you. I'd like to thank the organizers for inviting me to give a mini course here. I've never done it before. I've been to San Carlos 3 other times, I think. It's always a pleasure to be here. We had a very terrible winter in Boston this year. Winter here is much nicer. Much nicer. Pepe Ciade and I agreed that I would not come to his lecture, because even if I said some of the same things, if you just learned it 2 hours ago, it might be good to hear it again now. But I did come to the last 10 minutes of his to see where he ended, and I also asked people, and apparently there were no questions during his lecture. This is a course for students. You are supposed to ask questions. I want you to stop me and ask if you have a question. If my back is to you, don't just sit there with your hand up. Say loudly, "Excuse me," and I will try to answer your question or tell you I'll talk to you later. If you're an expert in the field, try to control yourself. Certainly if I make a mistake, tell me, that would be bad. But if you just feel like asking a bunch of questions that are of interest to experts and making a lot of side comments, seriously, control yourself. If you're a faculty member with students in the room, I would like to politely suggest that you leave. Your students will feel inhibited about asking questions. If you're sitting here, they will be afraid that they'll sound stupid. So I would suggest you leave. If you don't leave, I would suggest you yourself ask a really stupid question early so that they will feel more comfortable later. I wrote some notes for these lectures. They're on the conference website. I also put them here where I can update them myself. Yesterday, I found 3 typos in the math, not the English, in the math, and Terry Gaffney found one. I'm sure that there are more, so I will update them as people let me know about mistakes. If you find one, tell me. That would be good. Okay. So, I forget whose talk it was where they talked about high school algebra, and I didn't really agree that that was high school algebra, but I really do want to start in high school, and I'm not kidding. High school. Here, this is where y equals x squared. Definitely high school. We'll write that as y minus x squared equals 0. And yeah, in general, when I have a function f, like y minus x squared, I will write v of f for this set, v of f for the set, the vanishing of f, so the set of points where f is 0. High school, definitely. More high school. V of xy, where x times y equals 0. Either x is 0, y is 0. You get the x and y axes. Maybe not so high school, but it could have been. V of y squared minus x cubed. This is smooth at the origin. It's smooth, it looks like a little copy of R1 just bent smoothly, sitting in R2. This is not smooth at the origin. This is a singular point. There are two lines crossing. It does not look like a one manifold, an embedded, a one submanifold of R2. So this is a singular point. I realize that there are TV screens, but for people here, am I writing big enough? Okay, all right. A singular point, v of xy. So here, v of xy, not a smooth submanifold. And the same thing here. In fact, it's not even a topological submanifold. It's two lines coming together, even up to homeomorphism. It's not even a skip sub. It's not a topological manifold. Here, well, this is a singular point. It's not smooth, so this is a singular point. But the curve is, it's not smooth, so it's not a smooth submanifold. So, not smooth submanifold. However, it is a topological submanifold because topologically you can just kind of smush, it's a technical word, you can just kind of press this and project it to the y-axis, and it really is a topological submanifold. Now you may have, maybe you know, maybe you don't know. I plan to talk about the complex numbers. Sadly, I can't draw pictures over the complex numbers. Right? This is R2. The board is R2. It's not C2. But we want to draw something in the complex case. And so what we draw is the picture over the reals, even though it's misleading sometimes. So this is over the reals, but I want you to think of this now as x and y are complex. And it's still true that this will define a complex analytic submanifold of Euclidean space. It's true that this picture is kind of gives you the right feel. Things aren't quite right here. In the reals, this is a topological submanifold. In the complexes, it is not. That follows from Milner's work, but I'll talk more about it later. What's going on here? Why is this one smooth and this one singular and this one singular? You may not have seen the implicit function theorem this way before, but the implicit function theorem, so first let me write this equals the critical locus of f. So it's the set of points where all of the partial derivatives vanish. I only have two right now. So it's where the partial derivatives vanish. I try to be careful when I speak. That's a singular point of the set. This is a critical locus of a function. The two get used interchangeably for reasons that sometimes for reasons I'll discuss. But what does the implicit function theorem tell you? You probably only know it smoothly, and you know the analytic statement of it, unless you've worked in this for a while. But geometrically, it tells you if a point, if P, I tend to underline points and sheaves. If P is not in the critical locus, and P is in, and f of P equals 0, f of P equals 0, then V of F is a submanifold. Of, well, affine space. I'll just say a submanifold at P. So at means, you get used to this. If you've never worked in algebraic geometry, it takes a while to learn that when people say at, they usually mean in an arbitrarily small open neighborhood of. So it really means near. What kind of submanifold? It depends on what kind of F you have. If F is only C2, it's one thing, but I will always be talking about at least smooth functions, so a smooth submanifold of the ambient space, the affine space. Or really, I believe I'll talk about analytic functions all day, complex analytic ones. And there's a complex analytic implicit function theorem. And its geometric content is that if you are not at a critical point, then the hypersurface defined by the function is a smooth submanifold, complex analytic submanifold of affine space near that point. No questions? Pitiful, just pitiful. Good. Excellent.
Okay. So the thing that the difference, I'd like to understand this difference. In one, because you have a reducible polynomial.
Yes, here. Yes, it's true that any time analytic components intersect, you will have critical points. You will have singularities there. But this one is irreducible. So you can still have it. But yes, it's kind of more dramatic here. Is that?
So you just, by construction, I can get in any...
Well, I was trying to do something that you would have seen, that people would have seen in high school that had a singular point. So it was the easiest.
Singular points are different from each other.
Yes. Yes, they are. Even topologically, they are. Topologically, well, certainly over the reals, if you pull out this point, you get 4 connected components. If you pull out this one, you get 2. Over the complexes, if you pull out that point, things will still be connected. If you pull out this point, it'll be disconnected. So even topologically, those are different. But Milnor numbers, which Pepe Siade talked about, were you at Pepe's talk? Maybe you don't want to say. I don't know. Milnor numbers, which he talked about at the end, will distinguish them in kind of an algebraic way, which, part of the point of algebraic and kind of analytic geometry is that you can calculate. In my opinion, it's that you can calculate things that tell you about the topology. That's the point of looking at the topology of, the local topology of algebraic and analytic things. Did that answer your question? You don't look satisfied. Wait for it? All right. Okay. So do you have to have a singular point? So do you have to see something non-smooth in the set, in the hypersurface, if you have a critical point? So, right. If you do see something non-smooth, it has to correspond to a critical point. But do critical points have to give you non-smooth hypersurfaces? The answer is no, but for a stupid reason. I'm used to erasers being up there along the board. I'm frequently going to be looking for this thing. It's a stupid reason. And the stupid reason is that you might have squared this thing, or raised some factor to a power other than 1. So suppose you do that. Oh, look, V of F is the same thing. This is still V of f. But now every point is a critical point. Right? The critical locus of f is also V of f, V of y minus x squared. Every point becomes a critical point. This is annoying. We don't like this. So it is the usual assumption that f is reduced. Choose reduced. So that it has no repeated factors in its, well, the ring of convergent power series at the origin is a unique factorization domain. So you want no repeated factors other than units in that factorization. Let me just say reduced. There's an easy way to do this. So if f, so u will be open in Cn plus 1. To have a convenient point to talk about, I will have the origin in U. I will assume I have an f from U to C that is complex analytic. So this is complex analytic. This means it takes the origin to 0, so that I'm assuming that 0 is in V of f. And to avoid stupid cases, I want this to be non-locally constant. So not locally constant. And then choosing f to be reduced is the same as saying you don't want the dimension of the critical locus to be the same as the dimension of the hypersurface, which for us would be n. So V of f is n-dimensional. So the kind of geometric way of saying your function is reduced it's enough to say that the dimension at 0 of the critical locus of f is less than n. That'll do it. So these are same thing. All right. So now our question is, if f is reduced, all right, suppose f is reduced. So we haven't done the stupidest thing we can think of to create critical points even where the hypersurface is smooth. If f is reduced, then does a critical point necessarily give you a singular point on the hypersurface? The answer is yes. You need Milner's work to do it, so we will get there, but I just wanted, yes, this is my motivation. So, all right, I should say one other thing in this setup. I use coordinates z. So my coordinates will almost, basically I underline anything that's multi-component. So these will be my coordinates. Okay. All right. So maybe before I erase this, I should tell you one other thing about looking at the pictures over the reals to get an idea of what's happening over the complexes. You have to get used to this. In a minute, well, I'm going to intersect this with a sphere. And then you see these 2 points of intersection. Well, it's 2 points in the reals, but in the complexes, if this is complex 2-dimensional, the hypersurface is complex 1-dimensional, that's real 2-dimensional, you transversely intersect with a sphere, you'll get something smooth. It will be real 1-dimensional, it will be compact. So it's a compact 1-dimensional manifold. It has to be a collection of circles, and in fact it's one circle because this is one irreducible component. My point is that what looks like an S0, a zero-dimensional sphere in the real picture, you should always think of as an S1, a one sphere in the complexes. All right, I think I'm ready to do stuff. All right, so how do you, suppose you want to analyze the topology of the hypersurface at a critical point, so at a singular point on the hypersurface. This case is uninteresting. The implicit function theorem tells us everything we want to know about the embedded, so the local ambient, ambient means how it sits in the surrounding space, the local ambient topology of that hypersurface. It tells us that it sits there just like a copy of, well, R1 sits, an axis sits in R2, but now think in the complexes, it tells us that it's embedded just like a complex axis in C2. Very boring. This is the trivial case, the topologically trivial case. How do you analyze, how do you describe for someone anything about this situation that tells them, what can I say topologically about this singular hypersurface? Can I tell when two of them are different up to a homeomorphism that preserves the ambient space and the hypersurface? And so that's the fundamental question of the local topology of singular spaces, describing those, telling when they're the same, equisingularity conditions that tell you when they don't change in a family, something. So we want to do something topologically with this. So a first attempt, or not a first, the one we're going to think about the most is, all right, assuming we understand smooth things already, you try to reduce your singular problem to a smooth problem. So you intersect with a small sphere. Now, if you started with something with an isolated critical point, so it's the only critical point anywhere near there at the origin, then when you intersect with a small sphere, intuitively, you can see you get something smooth, and it's not, well, it's not so hard to prove that you get something smooth, depending on what you know. And so you can ask if this intersection of the sphere with the hypersurface tells you about the embedded topological type. And the answer is it does. So I will write S epsilon, all right, our ambient space, real 2n plus 2 dimensional. A sphere would have one less dimension, so. You intersect with V of F. Yes, I've drawn pictures of just curves in C2, but now I'm in the general, in arbitrary dimensions. This, I believe Pepe Ciade called this K, the real link. Yes? Where are you, Pepe? I saw you. Yes. Yes? Yes. The real link. And what you could hope is that the way that the real link embeds into the sphere, your hope, this describes the local ambient topology. That's your hope. And Wojciewicz's work, yes, that L with a slash through it is pronounced like a W, I'm told. So Wojciewicz's work tells you I can't possibly spell Wojciewicz. Crap. I didn't prepare spelling. It's in my notes, but so this is. And I don't know which way the slash goes. Yeah, whatever. Tells you that the cone, so this is the cone, on S epsilon intersected with V of F is the pair is homeomorphic to the closed ball. So this is the closed ball. The closed ball intersected with V of F. And for me, a cone on a pair will mean a triple that includes the base point. So the cone point goes to the zero. So this is the cone on two spaces is the cone on this, comma, the cone on this, comma, the cone point, and I'm saying that that's homeomorphic to this. So maybe I should write this at least once. By this I mean the cone on S epsilon, the cone on V of F, you identify their two abstract cone points and put the cone point here. And I'm saying that these triples are homeomorphic. So there's homeomorphism that sends the cone on the sphere to the closed ball, the cone, and at the same time sends the cone on the real link, right? This is K, to the hypersurface inside the ball and sends the cone point to the origin. In other words, the way that the link embeds into S epsilon describes the topology completely at the origin. Where? Oh, thank you. Thank you. Okay. It's time for another question. Who's got a question? You people are... crap. Well, if I can look, but that's cheating. I don't know how you spell it. And as I said, I'm not even sure I've got the slash going the right way. Okay, all right, good. All right. So we want to know how K embeds into the epsilon sphere. That would tell us everything. Well, but that means describing an embedding of one topological space into another one. Well, that's a lot. That's a lot of data. Also, I should have mentioned, if you didn't have an isolated critical point, so I should draw a non-isolated critical point, then the real link will not be a manifold. It'll be compact, but it itself will be singular. So if you take something like if you take something like this, yeah, that's probably as good as it's going to get. It has a critical locus that's the entire t-axis. So the critical locus here equals the t-axis. Something I forgot to say when I was telling you to ask questions. I can follow French talks if they speak French slowly. If I speak too rapidly, tell me. I can slow down. What I can't do is speak Portuguese. You can raise your hand and ask me to speak Portuguese. It's not going to help. Okay. This has a one-dimensional critical locus. When you take a small sphere around the origin, it hits the singular set of the hypersurface. So the real link there is not smooth. So when I say we'd like to understand how the real link embeds in the sphere, it's not just the problem of one manifold embedding into another one. If you're interested in non-isolated hypersurface singularities, it's the problem of some singular space embedding into a sphere. And that, of course, is a lot of information to encode in anything you can calculate. But before I tell you how you fix that problem, and I say you, meaning if you're Milner, how you fix this problem. I don't think any of you are Milner. I know what he looks like. Yes, I know none of you are Milner. But before I do that, I put exercises throughout my notes. And most of them, I really do think you should try. Most of them are straightforward, maybe not easy, but straightforward. But the first one I put in is probably the worst, and I don't want you to see that one and get discouraged. So maybe I should do one of the problems that I gave you. Can we analyze? This is very special. It may convince you that only in extraordinarily easy cases could we do this without some technology. I want to describe how this link sits inside this sphere for the cusp. Oh, this is called the cusp. I don't know what you know, cusp. Okay. So let's do this. I'll call it example, but it's one of my exercises. Okay. You can do this one, but you still have to know some things. You parameterize this curve. X equals t squared, y equals t cubed. Okay, well that was easy. Doesn't look hard so far. But then you have to intersect with a sphere of radius epsilon. Experts in the room. I needed you to say something. When I stated what would you say was his result, epsilon had to be arbitrarily small. For epsilon small enough, the cone on the sphere gives you the situation inside the ball. So maybe you always think epsilon is small, because that's how we use it, but I should have said it. Epsilon needed to be small enough. So this epsilon needs to be small enough. I should have said that before. Small enough. You need for there to exist an epsilon naught such that for all epsilon less than that one but greater than 0, these things are true. Small enough. It's not true for spheres of arbitrary size. Okay. That means, so for this intersection, we have to look at where, well, it's the norm of x squared plus the norm of y squared equals epsilon squared. Okay, I can do this. This is the norm of t to the 4th plus the norm of t to the 6th equals epsilon squared. And now you will have a problem that we give our first semester calculus students. Show that there's only one magnitude of t that there could be that satisfies this equation. I will do this calculus problem for you. Consider I'm lost for a function name, g. G of lambda equals lambda to the 6th plus lambda to the 4th minus epsilon squared. So epsilon here. We usually write is greater than 0 and in tech, That symbol is typed with /LL. I'm sure it stands for less than, but I always think of it as lots less. It's significantly small compared to 1. This is how we say things are small. Consider this. Show. G has exactly 1 positive root. Okay. G of 0 is negative. G of very big is positive. You know, as lambda goes to infinity, you certainly get something positive. It switches signs. G has a positive real root. So this tells you G has the intermediate value theorem, has a positive root. Root means place where something is 0. I'm sorry. I don't know if that's common. 1 positive 0. Has a positive 0, which sounds weird. Maybe that's why I should write root. And then how do you show it's unique? Well, G prime of lambda is 6 lambda to the 5th plus 4 lambda cubed, which is greater than 0 for positive lambda. So the function increases always for positive numbers, so it has exactly 1. Great. 1 positive root. Call it lambda naught. We've done our calculus problem. So, what does that mean x and y look like when you're parameterizing the real link? So t is lambda naught times e to the I theta. And then x is lambda naught squared e to the 2I theta. Y is lambda naught cubed e to the 3I theta. I will leave it here after saying this tells you that the real link is a trefoil knot. This is a trefoil knot. In S3. In particular, it's knotted. Why is it a trefoil knot? Because as theta goes from 0 to 2 pi, this goes around twice, this goes around 3 times. You see the trefoil knot. There's a little more to do, but this is the heart of the matter. You get a trefoil knot. It's knotted in S3. If we had the trivial ambient topological type, K would not be knotted in S3, but it is. Questions? Thank God you're here. I liked it, but it's about the only one. There aren't many you can do by hand like this without some theorems. I don't know what such a kind means, but okay. Some kind of critical point.
No, a cusp.
Well, you'd have to know what you mean by a cusp.
So then you don't know how to parameterize because the curve is not rational.
Every analytic curve in C n+1 locally breaks up into irreducible components, and each component has unique up to something parameterization. So you can parameterize theoretically. Doing it in practice can be hard, but it's a theorem that the parameterizations exist for each irreducible component. So no, you might, like we parameterize this. This isn't a collection of straight lines. You might have a number of components. Some look like this, some look like y cubed minus x to the fifth equals 0, but there could be more complicated things where you would have trouble explicitly writing down a parameterization. But the theorem is there is one, and it's unique up to, well, a bunch of choices, but is that?
Close to the singularity.
Close, yes, very close. All of this is local. The global topology is is a completely different flavor, which I rarely deal with. Some people do. If you take polynomials, not analytic maps, if you take polynomials, then you can look at their projective closure, for instance, and then look at what they define in projective space and ask about the topology of that. I am not talking about that today.
Let's understand this. You're saying that suppose that I have a curve, which is not genus zeros as such, but some genus 1 with some singularity. So you say that you can do the same business, the same kind of stuff.
Yes. In fact, it's a course. I don't really care how far I get. I really don't. I would rather answer questions. So let's take, maybe this will answer your question. You can let me know. Let's take y squared minus x cubed minus x squared. I drew, well, I just wanted to draw this. It does this. I'm not sure this will answer your question, but maybe it will. It does this. The global topology would include this loop. But locally at the origin, all you see is kind of two things doing this. It should look like two lines. It should. Does it? Well, yes. You can factor this like this. And this is, so what you get is y equals plus or minus x times, and then you pick one of the branches of 1 plus x. Because we're looking at convergent power series at the origin, this exists as a convergent power series. And this factors in the ring of convergent power series at the origin. Now, it's extremely unattractive algebraically. If you were trying to stay in polynomial land, you have to complete at the origin. But when you look at the ring of convergent power series, you can do nice things like this and leave polynomials behind, but it sure simplifies some things. And this is a unit. And so really what you see, because it starts with a non-zero thing, basically what you see are two lines crossing. And up to homeomorphism, that is what's happening there. Two complex lines are crossing. And you can parameterize each one separately. And did that answer your question? But if you were to parameterize it all at once, which you can do, I agree, it wouldn't be obvious to you that the real link is two disjoint circles that are then linked inside the sphere. It would be more problematic to show that then. But you could, you're right. And yes, there are lots of things that are, it's a theorem that you can parameterize it. That doesn't mean you can do it by hand easily. Yeah, but I'm only looking at the local topology, and things become, it gives us some techniques you wouldn't use in the algebraic case. All right? All right. That was good. I like giving this example to say why the convergent power series are nicer than the polynomial ring for local questions. Okay. So, as you can imagine, and as I was just saying, this is very special that you can describe the link inside the sphere so concretely. Don't say that to an engineer, this is concretely, but, so barehandedly without machinery. It is difficult to do this in general. And so the question is, how do you analyze the way the real link sits inside the sphere? And if you're Milner, you do the following. So, you don't write in yellow chalk. So, analyze. Okay, embedding into S epsilon. And if you're Milner, 1968. No telling when he actually proved it. This is just when it appeared. Probably 67, but 66, who knows. This is a lot of data. So describe instead the complement. So S epsilon minus the link. Now, of course, that doesn't tell you everything about this embedding, but it's a lot of data about the embedding. It's not everything, but it's a lot. And what you should have seen in Pepe Ciade's course is that, you look at this, put 2n plus 1 up here. If you take the map F divided by the norm of F down to S1, sitting here inside of C2, this is a locally trivial fibration. Smooth, locally trivial fibration. And that means, so this is the Milner fibration. He, of course, didn't call it that, but we do. The Milner fibration. And the fiber, and the fiber is the Milner fiber. So Pepe told me that he told you what a locally trivial fibration is, but let me just say it means for each point here, the inverse image looks the same. Actually, this is smoothly, so up to diffeomorphism. We care about homeomorphism, or even most of the time up to homotopy equivalence. A lot of things are true up to homotopy, and sometimes you can say things up to a higher level, and sometimes you leave it at homotopy theory. So each point, the inverse image of each point, looks the same up to things, up to diffeomorphism, homeomorphism, homotopy equivalence, and all that you have to describe the fibration is what happens to the fiber as it goes once around the circle. Such a thing is called a characteristic diffeomorphism or homeomorphism. It is not unique. But the induced map on homology is unique, or cohomology. And that's what people call the monodromy isomorphism. The monodromy isomorphism is the isomorphism induced on the fiber, induced on the homology or cohomology. By going once around the circle. Because I'll use sheaves near the end, and so cohomology. I wrote homology, but cohomology would make me happier. I don't know if it makes you happier or not. You still call it the monodromy isomorphism. Okay. Everybody with me so far? Who's trying? Questions from someone else? I'm happy with your questions, don't get me wrong. It'd just be nice if someone else said something. All right. This is not as manageable a characterization of the fibration as we would like. It doesn't compactify nicely. So the fibers here, I should say this though. What's the fiber here? The fiber is a, well actually, let me just do the other characterization first and then I'll discuss the fiber. But I will denote it by a capital F sub little f, 0, the Milnor fiber of F at the origin. This one is not so manageable. The fibers are not compact. If you try to close things to make them compact, they run into each other at the real link. And also there's a generalization of the Milnor fiber and Milnor fibration for arbitrary, where the domain is an arbitrary analytic space. John is not paying attention, proved by Lay, I don't know when. John, 30 years ago? Yeah, exactly. Never mind. Anyway, there's a generalization of this that applies to when the domain is an arbitrary complex analytic space, proved by Lay. But not in this form. So I should have said this. I'm going to write a big symbol. This is diffeomorphic. And I mean this thing, the whole fibration. So I'm going to write another fibration. So I mean the usual. That there's that there's a diffeomorphism of the total spaces and an obvious identification of the base spaces so that the diagram commutes. And Pepe was saying this at the end, I believe. He can tell me in a second. This is diffeomorphic if you take the open ball. So for me, that would be a closed ball. This is an open ball. And you intersect with F inverse of the boundary of a small complex disk and then map down to the boundary of that disk. So this, of course, is an S1. These are diffeomorphic vibrations. So the picture that everybody draws, and I draw, you'd think after all these years I would draw it better, but you'd be wrong. Let's see, will this show up? So you have a cusp. Here's the sphere. The inside is the ball. The Milnor fibration, this one, sits inside the sphere minus the link. And so I'm going to draw a typical Milnor fiber. A typical Milnor fiber. It wouldn't include this intersection point. And you're supposed to imagine that what I'm drawing is up on the sphere somewhere. So there's some Milnor fiber up here on the sphere. This one, you take what Pepe was referring to as a Milnor tube, I believe. So you take a small disk. Yes. It's important how you choose things here. Delta is chosen small compared to the value of epsilon, which of course is arbitrarily small. So in the picture, that would be that would be here. And you're supposed to imagine that's inside the ball, so maybe I should make it look more like it's inside by doing that. So you should think of this distance, but it's not the distance. The value of F is delta, and it's inside the ball. And what Milnor, in fact, let me make the orange smack into that, because that will let me say what I want to say. What happened to the orange chalk? Part of what Milner does is proves a little lemma that for the Milner fibration on the sphere, you'd get the same thing if you took out the link as if you took out a small neighborhood of the link and stopped here instead. And then Milner gets this, I believe Pepe said this, by integrating a vector field, either, well, inward or outward, depending on which way you want to go. I honestly don't remember which one Milner does. But you integrate a vector field to take the whole ball down to this tube. So the tube that people talk about and that Pepe was talking about is where you put in the whole disk. So that's this, all of this filled in, but then you just take this part, the boundary, and so it means the Milner fiber here, there the Milner fiber is, it's got the norm of F in it. It's really yuck. And over here it's, I take an open ball and I intersect with F inverse of a small number, where A is some complex number greater than 1. I mean, greater than, that's not 0, and is some small thing less than epsilon. So this just presents the Milner fiber as a deformation of what happens when A is 0, right? When A is 0, you've got a hypersurface inside a ball. You let A be something small, not 0, you get the Milner fiber. So it's a deformation of the hypersurface. And this one compactifies nicely. And if you've ever done any topology, you know that studying non-compact manifolds with boundary is, so let's try that again. Studying non-compact manifolds is worse than studying, I'm going to try it one more time. Studying non-compact manifolds is worse than studying compact manifolds with boundary. So you compactify. How do you do that here? Wait, watch, it's easy. There, it's compactified. And you include these points. Now your Milner fiber just changed. Your Milner fiber before was a manifold, actually a complex manifold, right? It's a complex, just like V of F itself, it's complex. So this too, this is what we usually call the Milner fiber. It is complex, a complex N manifold, but it's not compact. A complex N manifold. So this is the complex dimension. It's a complex N manifold, but it's not compact. When we close it and take the closed ball, you get, well, a real 2N manifold whose interior is a complex manifold, but it has boundary now. Well, that's okay. We can live with that. So, and up to homotopy, those are the same. So if all you care about are homotopy questions and homology and cohomology, it doesn't matter whether you include the boundary or not. If you've seen collared neighborhoods of boundaries, that's why. If you remove the boundary, you have the same thing that you started with up to homotopy. So up to homotopy, we don't care whether we're dealing with the compact Milner fibration or the non-compact one, and compact things are nicer to deal with. So usually I'll mean this one. So that's the closed ball. Everybody with me? Questions? All right, I think that's all the stuff that I can do without looking at my notes. Because I want to list 10 properties of Milner fibers and fibrations, and there's absolutely no chance I would get them in order without looking. So these are the order in which they appear in my notes. I am not planning to prove any of these for you. I don't know how many of them Pepe will prove, but let me tell you the properties that I want to tell you. I should say that while Milner spends a lot of time on isolated critical points, the fibration exists for critical points of arbitrary dimension, and I will hopefully be clear in what I state, which things are true in general and which are not, so properties. Of Milner fibers and fibrations. Okay, 1. This one is supposed to be obvious. If 0 is not in the critical locus of f, well, then we know the implicit function theorem tells us everything is trivial. Well, then is diffeomorphic to a ball an open ball, if I mean the open fiber, which I do. Then, this time, is diffeomorphic in particular. It's contractible and has trivial homology in particular. It is contractible. That was exciting. If that weren't true, Milner fibers would be utterly worthless. 2. The Milner fiber has the homotopy type. So I write this for homotopy equivalent. To a finite n-dimensional CW complex. I need to be careful. When I was learning this stuff, I was frequently confused about which dimension people were talking about, even when it should have been clear to me. Frequently, I'm talking about the complex dimension, but this is its dimension as a CW complex. It means its real dimension. At least I don't know of something that's called the complex CW complex. Finite n-dimensional CW complex. In particular, H, all right, remember, this is n-dimensional, but that's complex dimensional. So this is, I want to emphasize this right now. Complex n-dimensional, or complex dimension equals n. In particular, I will always use integral coefficients. So this is the last time I intend to write this z here. I always mean integral coefficients until I have complexes of sheaves there. And then, well, then nobody will be in the room. This is free abelian, a finite rank, free abelian, and Hj in the Milner fiber is 0 for j greater than n. This should not seem obvious to you. If it seems obvious to you, either you know most of this stuff already, or you're confusing the real dimension and the complex dimension. This is complex n-dimensional. This is a 2n-dimensional real manifold, real 2n-dimensional manifold, and yet it has no homology above dimension n. So people refer to dimension n as the middle dimension, so half its real dimension. It has no cohomology above middle dimension. Right? I mean, if there were 2 in here, maybe I'd agree this is obvious, but it's not. All right. I like to call the dimension at the origin of the critical locus S. Sadly, my printed S's look like the number 5. So I will use one of my cursive S's, one of my handwritten S's. This is what I always use for the dimension. Critical locus of F. Okay. So 3 is Milnor fiber of F is N minus S minus 1 connected. So when S is 0, Milnor proved this, and it's something Pepe said. When S is 0, so you have an isolated critical point, it is N minus 1 connected. And then because it's a finite dimensional n-dimensional CW complex, and it's N minus 1 connected, general theorems on topology tells you that in fact it has the homotopy type of a wedge of spheres. So S equals 0. The dimension of the critical locus at the origin. It just doesn't look like an S. It doesn't look like a 5. It just doesn't look like an S. The Milnor fiber of F at 0 is homotopy equivalent to, this is the 1-point union, a wedge. Of SNs, of a finite number of them. And the number of them is usually denoted by mu, and is, so this is S equals 0, where mu equals mu sub 0 of F. It's also written, depends on whether you're changing the point or changing the function. It's also annoyingly written, well, not annoyingly, I switch back and forth depending on which one I'm emphasizing. So this is the Milnor number of an isolated critical point. Oops. It's the number of spheres in the homotopy type. For general S, this was proved by Kato and Matsumoto. It follows from a result of Lay's, which I intend to sketch the proof of next time after we've seen some Morse theory. Oops. I see this part was number 4. This was my property 4. Suppose that S equals 0 has a homotopy type. It's called the Milnor number. Yes, okay, fine. That's property 4. 5. I like analytic geometry because I can calculate things algebraically. I have some hope of calculating things algebraically. Milnor proves that in this case, that the number of spheres is the degree if you take the complex gradient vector of F and divide by its magnitude and look at it as a map from a sphere to a sphere, then because S is 0, when you look on the sphere, you have no zeros, so you can look at it as a map from the sphere to the sphere. The degree of that map, the topological degree, is mu. He doesn't actually state the apparently well-known result of that. I'm told that it was known at the time that that was exactly the same as, so if S is 0, this Milnor number, and Pepe also wrote this, is the dimension as a complex vector space. This is not the Kroll dimension. The Kroll dimension of what I'm about to write would be 0, of the ring of convergent power series at the origin modulo the Jacobian ideal. This will be a finite dimensional vector space. This will be a finite dimensional vector space. And for easy examples, you can calculate this by hand. And for hard examples, you can calculate it with Singular or Mathematica or your favorite computer algebra system. All right. But easy examples can be done by hand. If I don't run out of time, I will calculate some by hand. There are exercises for you to calculate some by hand. About the exercises. If you try them and you have trouble, ask me. Maybe not in here, but outside of here. Yes? Well, yes, because otherwise there's not going to be a single number. You can talk about the Betty numbers, right? In general, if S is bigger, yes, maybe I should say, this result and this result tell us that, in fact, I'm glad you asked that, because the interesting cohomology of the Milner fiber, so this is reduced, or I'll put I, homology of the Milner fiber. This is 0, well, let me just write, is 0 unless, so the only place it might not be 0, this is 0 unless I is between n minus s and n. So this is where it's conceivably non-zero, so maybe that's a better thing to write. Can be non-zero only if so that, yes, when s is 0, there's only one interesting degree, and you can ask for the rank of that homology group, and that's the Milner number. As soon as s is something bigger, like 1, you get homology groups, and you can get homology groups in more than one dimension. And you can ask for the Betty numbers. No one knows how to calculate that in general. You can do it for specific examples, but in general, no one knows how to algebraically calculate the Betty numbers of the Milner fiber. Now, what you can hope for are some bounds. You can, and that is what the Ley numbers will give us later, but the only time things are really easy in quotes, algebraically, is for an isolated critical point where you can do this. The rest of the homological data about the Milner fibers of non-isolated singularities is dramatically more complicated. All right, that was 5. 6. I'm stating 6 and 7 so that you have some hope of calculating things in interesting cases. They won't be of use to me later in my lectures, but for you to calculate, well, some of my exercises, and just for, if you really are going to work in this area and want to produce examples, it's nice to have some tools for calculating. So, 6. Breaking chalk just means it's humid. I learned this a long time ago. It's humid in here. If f is a weighted, so this is in Milner's book, a weighted homogeneous polynomial, the Milner fiber of f at 0 is diffeomorphic to f inverse of 1 inside all of Cn plus 1. So you can take the global fiber over 1, and it will look the same as if you took a small ball and took a small value of f. So this can be useful in actually analyzing Milner fibers of weighted homogeneous polynomials. Yes. 7. Okay. Well, that's a stupid way. I'm sorry. I have to make a note to myself to fix something. What I state for 7 is not wrong. It's just not the way I want it. Just have to make this little note to myself. If you're looking at my notes, what I do is I now take two polynomials, or two analytic functions with the same number of variables. That you should allow the case where they have a different number of variables. Oh no, my vision jumped to number 8. No, I think 7 is fine. Okay, ignore me, thank you. So suppose I've got two functions, f from u0 to c0. So I've got two of these. I'm hurrying now to make sure I finish my statements. I speak slowly. And a u prime that may be in a different copy of affine space. All right, you should think of as in a different copy of affine space, but it could be a different dimension. So this is fine, n+1 dimensional, but just anything. This is an open neighborhood of the origin in affine space of any dimension. And you can ask about the Milnor fiber. Let's form a new function, h. Define h of zw to be f of z plus g of w. All right, so this will be h goes from u cross u prime to c. Then, so you've put together two functions, but they're usually referred to as in disjoint variables. So there are no overlapping variables. Then the Milnor fiber of h, at the origin is homotopy equivalent to the join of these Milnor fibers. So this is the join. This is the Sebastiani-Thom theorem. Sebastiani-Thom theorem. Proved by a number of people in a bunch of different cases. Matsuo Oka proved one. I think he's here, yes. I can't keep track who did which case. But this is useful. It tells you about the cohomology, and so that I can write it the same way I wrote it. If you don't know what the join is, there's an appendix in my notes that describes some things like cones, but the curve selection lemma. But it also, I define the join, but what's relevant for us at the moment, or for calculating Milnor things, is that the reduced cohomology of the join of two spaces. I'm not writing a property of Milnor fibers now. I'm telling you what this tells you about the homology, is the sum of k plus L equals j of h tilde k of x. The tilde is reduced homology, tensored with h L of y, direct sum, well, the Tor part. There's always a Tor part. I should say, you can do all of these things with field coefficients if it makes you happy. And then, of course, the Tors will go away, but then you lose information. So why do that? Well, so the point of my writing that formula isn't, quick, memorize that formula. It's that, yes, knowing the cohomologies of these Milnor fibers tells you the cohomology of this Milnor fiber. All right. 8. Is he paying attention now? I can't tell. Yes, he is. All right. So 8, I state in its kind of best form, but now I'm just going to say it quickly. The homotopy type of the Milnor fiber, well, let me just say of F sub F. If F is reduced, is an invariant of the ambient topological type. Of V of F. All right. In fact, the whole Milnor fibration, up to homotopy, is an invariant of the local ambient topological type. So I'm saying if you have two hypersurfaces, and you have reduced functions defining them, so F and G, and the two hypersurfaces have the same ambient topological type at the origin, so there's a homeomorphism of triples, an open neighborhood of the origin, an open neighborhood, that open neighborhood intersected with the hypersurface, comma, the origin. There's a homeomorphism of triples, taking one of those to the other, then the entire homotopy type of the Milnor fibration are the same. In particular, the homotopy type of the Milnor fibers are the same, and you can pick a homotopy equivalence that commutes with the monodromies. This is good. Of course, if S is 0, this follows from Milnor's work, because the homotopy type is completely described by the Milnor number. For general S, it was proved by Ley, 30 years ago. It's very important. We'd like to know, if we're trying to analyze the local topology of a hypersurface, we would like to know that the things that we calculate only depend on the local topology of the hypersurface. Or I'd like to know that. I don't know about you, but that's what I'd like to know. All right, there are two more things I want to state. And then I could stop or calculate an example of Milnor numbers, but suppose 0 is a critical point, and let TIF, do I really write all of this? Yes, I do. Be the monodromy isomorphism. Okay, in degree I. So, then the Lefschetz number of the monodromy is 0. This is a Campos result from 30 years ago. Then the alternating sum of the trace, the alternating sum, yes, the alternating sum of the trace of is 0. You may wonder, I'm not going to spend much time at all on the monodromy, mainly because I don't like the things I can calculate about it. I'm not satisfied with anything I can do with the monodromy. However, why do I want this result on the board? We know that if you have a singular point on your hypersurface, that you must have been at a critical point. I would like to know that if I'm at a critical point, then I must see a singular point on the hypersurface, that the hypersurface is not embedded trivially, topologically, in space. In particular, that would, I want to know the Milnor fiber is not contractible. That would detect it. I want to know it goes both ways, that critical point implies Singular point on the hypersurface. Singular point on the hypersurface implies critical point. For reduced functions, reduced. For isolated critical points, it follows from that calculation of the Milnor number. For non-isolated critical points, how do you know that the Milnor fiber at a singular point is not contractible? The way I know it is from this. If the Milnor fiber were contractible, this Lefschetz number, oh, this is the Lefschetz number. The Lefschetz number would be 1. It's not. It's 0. The Milnor fiber is not contractible. So things are not topologically trivial. It is not homotopy equivalent to a point. Well, it doesn't even have the homology. It doesn't even have the homology of a point. Understand then, so that is 10. 10 for me is, as always, I'm assuming F is reduced. Zero is a critical point if and only if the ambient topological type is non-trivial. I have two things to say about this. We already saw this is not true over the reals. The cusp over the reals has a critical point at the origin. And it's not a smooth submanifold, but it is a topological submanifold. That does not happen over the complexes. Right? There's a very strong dichotomy here. You may wonder, what do I mean by a singular point on a hypersurface? What do we mean? Do we mean, oh, it's not complex analytically a submanifold? Do we mean it's not smoothly a submanifold? Or do we mean topologically it's not a submanifold? We can be as strong in both directions as we want. The two cases are huge, completely opposed to each other. If 0 is not in the critical locus, implicit function theorem, you have a complex analytic submanifold. The strongest way you could mean you've got a submanifold, you've got it. It's as trivial as it could possibly be. On the other hand, if F is in the critical locus, it's as bad a non-submanifold as you could have. It's not even topologically a submanifold. Forget smooth or complex analytic. It is not topologically a submanifold. This is true for hypersurfaces. It is not true for analytic spaces of higher codimension. But hypersurfaces are nice. And this stuff follows from all the work on Milnor fibrations and Milnor numbers. Rather than go over time by calculating some Milnor numbers for me, I want to emphasize you should try the exercises and ask me or somebody outside of here how to do them if you're interested. If you're not interested, I assume you won't talk to me about it. But if you're interested, ask me. I'm happy to talk to you about it outside of here. I don't think I'll do the exercises in here. Tomorrow, I want to discuss a little Morse theory. I don't know how many of you know Morse theory, but the main tool that Milnor uses for analyzing the topology of the hypersurfaces is Morse theory. And if you've never seen it before, it is certainly very cool. And I will sketch a proof, not Milnor's proof, that for an isolated critical point, the Milnor fiber has the homotopy type of a bouquet of spheres, and how you count the number of spheres. And I will also prove a result of Lay's, which in my opinion, I keep mentioning that guy. I will mention a result of Lay's, which in my opinion was I'm going to offend somebody, was the only good result for calculating things about Euler characteristics and bounds on Betti numbers for Milnor fibers of hypersurfaces with non-isolated singularities. I always call it Lay's attaching result. It comes from his paper. The title is in French, but it's calculation of the number of vanishing cycles. I want to go through that proof because once you understand sketch it. Once you understand Morse theory, it's actually very simple, but you have to understand Morse theory. It's also only very easy if you leave out all the technical details and just give the flavor. All right, you guys, I want more questions tomorrow. You were awful. You were a bad class. You're very bad. All right, thank you.